Hello friends, welcome to Coding Interviews channel. Hope you are doing great. If you haven't subscribed to the channel yet, please go ahead and subscribe. I have created bunch of playlists to cover various categories of problems such as dynamic programming, greedy method, BFS, DFS and so on. Please check them out. I have uploaded the code for this problem to the GitHub repository. You will be able to find the link from the description section below this video. Let's jump into today's problem. Power of 2. Given an integer, write a function to determine if it's a power of 2. So we are passed with an integer, right? So and we have to determine whether it is a power of 2, right? So let's actually examine like some of the powers of 2: 2, 4, 8, 16, 32. So what actually makes a number power of 2, right? So one thing or one way that we could say is if we continuously divide a number by 2 and if the final result is 1, right, that means that number is power of 2. So for that example, right, we could say, okay, let's say the given number is 32, right? So what we are saying is divide it continuously by 2, right? So 32 divided by 2 will be 16, and divided by 2 is 8, and divided by 2 is 4, and divided by 2 is 2, and divided by 2 is 1, right? So if we are able to use this division and get it to 1, right? So basically at every division we should see the result should be 0, right? So basically if we divide a number by 2, that means there is no residual. It should be evenly divisible. For example, if we take a number 32, right, 33, right, 33 is a number, then if we divide by 2, we won't be actually able to divide it by 2 without any residue, right? So what we are saying is the modulo, right, 33 mod 2 should be 0, right? If any time number modulo 2 becomes 1, right, so that means we won't be able to get to number 2, right, at the end result, or the end result is number 1. So at any time it is not equal to 0, right, at any stage while dividing by 2 for the given number, right, at any stage if it becomes not equal to 0, the number percentile 2, the number mod 2, right, is not equal to 0, then we would say, okay, it cannot be what do you say, a power of 2, right? So that's a good way to assume. Let's say for a number like 55, right? So 55 percentile 2, so probably let's take 54, right? So 54 percentile 2 is 0, right? So let's say it is 0, and next what we are going to do, 54 by 2, that means 27, right? So 27, but percentile 2, is it really 0? No, right, it became 1. So that means 54 cannot be power of 2. So likewise, the only time when you should see a number percentage 2 is equal to 1 is when number is 1. That's it, right? When number is 1, that is the only case we should see number percentage 2 is equal to 1, number mod 2, basically when I'm calling as percentage, but it is number mod 2 is equal to 1. So when n is equal to 1, that is the only case we should see it. So this is one of the good ways to solve this problem. So this is one thing. So this is one approach, right? So we'll look at like 3 different approaches and then we'll go look at the code. So this is one approach. So we have been continuously dividing the number by 2, and if we get the result 1 at the end, right, that's when we say it's number 1. And let's actually look at different kind of representation, right? So let's look at them, all these things, all these example numbers, by converting into binary representation. So what is a binary representation of 2? It's 1 0, right? So what is the binary representation for 4? 1 0 0. What is for 8? 1 0 0 0. What is for 16, right? So what is for 32? So this is the binary representation. So that means when you really look at them, right, the binary representation of the given number, right, so you only have single one and rest of them are zeros. That single one is at the MSB, that is most significant bit, right, from the left side, right. So when you look at from left to right, only the leftmost bit is 1 and all the other bits are 0. So what does this tell you? So this is another way to look at, although there is a similarity between our first approach and second approach, right. So what we are saying is we convert the given number into binary and see if the number of ones are just 1, right. So we converted the number to binary and then count number of ones, right. So it should be is equal to 1, then it's a power of 2, then it's a power of 2, otherwise it's not, as simple as that, right. So this is our second approach, right. So you just convert the number into binary and then count the number of ones, right. So if after all these two approaches, right, there is another method that we could look at is, okay, this will be a bitwise manipulation. So basically a bit manipulation. So if a given number is n, let's say, right, if given number is n, right, so by using the bit manipulation technique we will be able to identify with a single operation. So let's apply n and n minus 1, right. So that let's apply that, right. So n is equal to 3, sorry, n is equal to 4, let's say, right, n is equal to 4, right. So 4, what is the binary representation? 1 0 0, right, and n minus 1 is what? 0 1 1. So what we are going to do is an AND operation. So this is a bitwise AND, right. So if you do a AND, right, what will be the result? AND will be 0 0 0, right, because AND for AND, right, 1 1 will be 1, but 1 0 will be 0, right, and 0 1 will be 0 and 0 0 will be also 0. So this is a AND truth table, right. So this is, we will call this as truth table for AND, right, truth table for AND, right, what we call, right. So that's what it is. If both of them are ones, then only we will return 1 in case of AND. So that's what it is. So 1 0 is 0, 0 1 is 0, 0 1 is 0. So this will be, the result is 0. So what we will say is, okay, when n and n minus 1 is equal to 0, that's a power of 2, power of 2. So I took a number 4, right. Let's try to do that with 5, right. Let's try to do that with 5. Let's say n is equal to 5. N minus 1, what will be n minus 1? 5. So 5 is what? 1 0 1, right. 4, n minus 1 is 4. So that will be 1 0 0, right. So when you do AND of 5 and 4, what it will be? 1 0 0, right. So in this case it is not coming as 0, that's why number 5 is not a power of 2, but in this case number n is equal to 4, it was satisfied, right. So n and n minus 1 is equal to 2, that is a power of 2, right. So basically what we are saying is, we just take a number and subtract that number by 1 and do a bitwise AND. If the result is 0, then we were saying it's a power of 2, otherwise it's not a power of 2. So those are the three methods that I wanted to show you. Let's go ahead and look at the code for this particular, for all of them basically. So we will see three different methods, okay. So the first one, right, so is power of 2, we are passed with an integer n. If n is less than or equal to 0, we will just say, okay, return false, we don't have to do further. But while n is greater than 0, what we are doing is n percentage 2, that means n mod 2 is equal to 1 and n is not equal to 1. So what we said is, in the first approach, n mod 2 is not equal to 0, right. If n mod 2 is equal to not equal to 0, the only place or the only time when should be n mod 2 is equal to 1 when n is equal to 1, right? So that's what we are checking for. So n per mod 2 is equal to 1 and n is not equal to 1, then we immediately return false. We don't have to look further. For example, the case is 33 by 33, right? 33 percentile 2 is 1, so we immediately return, right? We don't have to go further. For example, 54, right? We first go through one iteration, and when it becomes to 27, we check, okay, it is not, then return false immediately, right? We don't have to go further, right? So this is one method. So basically you are checking whether n percentile 2 is equal to 1 and n is not equal to 1, then return false. But once you come out of this, right, that means it did not see this case, that means the number must be power of 2, then you return true, right? So for each iteration you are decomposing n to n by 2, right, like that, right? So that is our first approach. And the second approach is we are counting the number of ones, right? So we are counting the number of ones. So if n percentage 2 is equal to 1, just do the count of number of ones. So initially the count of number of ones is initialized to 0. So the initial condition remains the same. If n is less than or equal to 0, you will just return false. Otherwise we enter the while loop. Before that, just initialize the count of ones. So finally we are trying to decompose the number and trying to get the number of ones. So to make this little bit faster, I am checking if the count of number of ones is greater than 1 here itself as part of the while loop and returning it from there and there itself. But if you would like, you can just comment this section and go on, right? So go on, and then while you come out of that loop, right, finally check if the count of number of ones is 1. Otherwise if it is 1, then it will going to return true, otherwise it is going to return false, right? So this is another simple method, right? And then so going down, so this is the third method. Basically we are passed with n and this condition remains same. If n is less than or equal to 0, we just return false. Otherwise what we are saying is n and n minus 1. This is what our bitwise AND, right? So this is what bitwise AND, right? So if you do that, if the result is 0, then we are good, that is the power of 2. If the result is not 0, that is not a power of 2. So that's what we are able to come up with the solution, right? So there are 3 different solutions that we have showcased here, right? So now let's go ahead and look at the time and space complexity for them, right? So time and space, right? So what is the time this is going to take? So we have been decomposing this n to n till n by 2, but in worst case how much time it will take, right? So for example, if the number is really a power of 2, right? So if you give like 128 or 256 or 1024 or 4096, something like that, right? So how many times this is going to take? So we have been dividing the number by 2 each time. So this when we are saying the search space division by 2, right, there is one intuitive algorithm, right? So the intuitive way for this is, okay, whenever you are dividing the search space or a number by 2 continuously, right, so you are dividing the search space by half. So that means the total time complexity will be equal to log n time, right? Log n time, where n is the given number. So this is going to take the log n time, right? And what about the space? Are we using any extra space here, right? So that's the thing we have to think. So we are not using any extra space here. So that means order of 1, right? So that is a constant space, we would say, right? So for our first approach is a log n time and order of 1. So log n is the worst case time, only for the powers of 2. So between the integer range, right, at least in C#, right, int 32 bit, right? So that range is only, there are only 32, there are only 32, right? There are only 32 integers which are divisible by which are really powers of 2. So if you take 2 power 32, right, that's what I am saying. But anyway, so if you go to the edges of it and maybe the final conditions, right, it will be only 31 integers, right, which are really power of 2. So only for those 31 it will be log n, but all others it will be much quicker than log n, right? So that's the first approach, time complexity and space complexity. Let's go look at the second one. So here also, similar to the first one, we have been doing the similar way, right? We have been decomposing the number into 2, right, and then coming up with a count of number of ones. So basically here the complexity also is equal to the log n, and the space complexity, we are using one additional variable here which is called count of number of ones, but this is just one single variable irrespective of the number that is given for you. So here even the second approach, we will say the time complexity will be equal to the order of log of n, and the space complexity is equal to the order of 1. So constant space. So between the first and second approaches, the time and space complexity is not different, right? So but we can definitely see the first approach will be faster than the second approach for most of the cases except those 32 numbers, right? And then moving forward with the third approach, so how much time and space complexity we are going to need here. So time complexity, so we are doing n and n minus 1. So this is a bitwise AND of basically two numbers, right? So normally when you say, okay, when these operations are there, we would assume they will be done in a constant time, right? So if you subtract the number 1 from the given number and then do an AND operation. So it actually depends on how many number of bits are there in the AND operation, right? So given how many number of bits are there in n and how many number of bits are there in n minus 1. So most likely if there are 10 bits in n, there can be 9 or 10 bits in n minus 1 as well, right? So that's the reason why we will say this will be in the order of bits in the n, right? So that will be again, so how many number of bits are there in n? So it will be coming down to the log n anyway. So there are two ways to look at it. So the number of operations per se for AND, it will be saying, okay, it will probably take a constant amount of time, right? So that's what one way to look at it. But in terms of n that is given as the input, right, how to give the time complexity, you should say, okay, it probably is in the order of the number of bits of n. So but how many bits will be there in a given number? It will be log n, right? So log n bits will be there in a given number. So we would say, okay, the time complexity for this also will be a log n. And what is the space complexity? Obviously there is no space that extra we are using, so it will be a constant space complexity. So for all these algorithms, right, instead of log n, we could say it will be equal to since it is an integer range, right, so it is the order of 32, right? So in all these cases, this is, we are trying to calculate how many times the maximum number for an integer range is 32 bits, right? So 2 power 32. So that means this would be executing the max 32 number of times, this while loop. So it's the same thing for this also. And what we said in the third approach is that it equal to the number of bits also, right? So that will be 32 bits anyway, right? So if you want to say log n, that is one way to look at it. But if you want to say order of 32, right, that is also another way to look at it. So if you want to say order of 32, that will be equal to the order of 1, right, basically the constant time, right, constant time. But even though we are saying constant time for all these algorithms, there is a slight difference between those, right? So the point I want to convey here is, for this particular algorithm, the time complexity, there are multiple different ways to look at it. So since it is just a number given and that is an integer number, so you can say log n, that is also correct. But if you say 32, order of 32, that is also a correct answer. But if the number integer range is different, then 32 becomes wrong answer, right? So if it is int 64 or a long or something like that, right, then the complexity is going to increase. In that particular cases, then you would say log n is the right answer. So these are like several different ways to say the time complexity for this particular algorithm. But anyway, for all of them, the space complexity is just constant. So it is order of 1. So if you have any further questions, please post them in the comment section below this video. I have posted the code to GitHub repository. You can find the link in the description section of this video below. If you haven't subscribed to the channel yet, please go ahead and subscribe and share among your friends as much as you can. Please click on the bell icon so that you will be notified about all my future videos. Thank you for watching. I will be back with another problem very soon. Till then, stay safe. Goodbye.